Hey, back for more. We're ready to continue our discussion of anharmonicity and its impact on infrared spectra. Okay, so we're going to draw an infrared spectrum here where the horizontal axis is going to be represented by the wave number associated with an infrared transition between vibrational levels. And in this diagram, wave numbers are increasing from left to right. That's why we have this little arrow here. So low wave numbers on the left, high wave numbers on the right. We're also plotting intensity of the transition or absorption associated with the transition, such that a stronger absorption is going to go higher along the vertical axis. This is, of course, different from what you actually see when you do an infrared spectrum in the lab, and we'll look at some examples of that in a few minutes. So, suppose we have an infrared spectrum that shows two peaks corresponding to two separate absorptions and two vibrational transitions. In this case, the larger of the two peaks at higher frequency, again remembering the higher frequencies are to the right, corresponds to the 0 to 1 transition. And as we noted earlier, according to the equations from our last video, the wave number frequency associated with that transition is going to be equal to this expression here, nu e minus 2 nu e xe, xe again being the anharmonicity constant. The lower of the two transitions corresponds to 1 to 2, and in this case again, using the equations from the previous video, we'll see that that is equal to nu e minus 4 nu e xe. And again, always note that the 1 to 2 transition is going to be lower in frequency than the 0 to 1 transition, because the spacing between the 0 to 1 levels is less than the spacing between the 1 to 2. So here we have again, this one corresponds to the 0 to 1 spacing, and the 1 to 2 transition corresponds to this equation. And again, the 1 to 2 is less than the 0 to 1. And of course, the 2 to 3 is less than the 1 to 2. So it just keeps getting smaller and smaller as we go up the ladder. The other thing to note, of course, is that the peak corresponding to the 0 to 1 transition is higher than the peak corresponding to the 1 to 2 transition, and that's simply a matter of population. There are far more molecules, as we noted in an earlier video, in the n equals 0 state than is in the case of the n equals 1 state. So since there are more molecules to undergo a 0 to 1 transition, we'll see a higher peak for the 0 to 1 transition than the 1 to 2 transition. Now, important thing to note is the spacing between these two lines. If you take the wave number values for each of these particular lines, and you take the difference between the two, we're going to note that the difference between the two is equal to 2 nu e xe. And that actually will always be the case if we were to add to this, for example, a transition corresponding to n equal 2 to 3, which would be at even lower frequency, and of course the intensity would be even lower, as we noted before. We would note the same thing, that the spacing between the 2 to 3 and the 1 to 2 would also be equal to 2 nu e xe. So that spacing is important, because that spacing is going to allow us to calculate the anharmonicity constant x sub b. So we note again that according to the anharmonic oscillator, we're going to get a different frequency transition for each of these bands. 0 to 1, 1 to 2, 2 to 3 are going to occur at different frequencies, and we're going to see a separate IR peak for each one. Again, remember, for the harmonic oscillator, it would predict that they all occur the 0 to 1 transition, the 1 to 2 transition, the 2 to 3 transition will all occur at the same frequency. So according to the harmonic oscillator, we'd see only one peak rather than 3 as we see here. This, of course, is more accurate. The reality is we will see 3 peaks or more if we have sufficient populations in these levels. And we'll talk a little bit about that later on. But in this case, we see a distinction between the harmonic oscillator and the anharmonic potential. And the anharmonic potential provides a better description of the molecule and a better description of the spectra that we will see. All right, so let's take a look at selection rules associated with the anharmonic system. You'll remember that the selection rule for the harmonic oscillator was that delta n was equal to +1 and there were no exceptions. In the anharmonic oscillator, we'll note that delta n equal +1 will always be the strongest transition, but we can also have delta n of +2, +3, etc., which are absolutely forbidden according to the harmonic oscillator, but these can show up. Remember, these were called harmonics. These can show up in the infrared spectrum. They're just much, much weaker, meaning the peaks are much lower in these situations for these transitions than is the case for delta n plus 1 for the delta n plus 1 transition. And we're going to note that that means that, as I said, they're not forbidden and they are allowed. Okay. The dissociation limit spacing, that is what we're talking about here, is the spacing of energy levels at the dissociation limit, shown here. Because we have above the dissociation limit no energy levels, what we call a continuum, that means the spacing between energy levels is going to be equal to 0 at the dissociation limit. Okay, so we talked about in the previous slide where we looked at an infrared spectrum and we saw the 0 to 1, the 1 to 2, the 2 to 3 transitions. We talked about those showing up. We will note that those transitions that originate from levels above n equals 0, that is the n equal 1, 2, 3, etc., those transitions that originate from those levels are referred to as hot bands. And the reason they're referred to as hot bands is because at room temperature, for most vibrations, the vast majority, the huge majority of molecules exist in the n equals 0 vibrational level. So the vast majority of transitions are going to come from the n equals 0 level. And in many cases, there's so few molecules in the n equal 1 level, we won't even see a 1 to 2 transition in the infrared spectrum. In order to see a 1 to 2 transition, we have to heat the sample to higher temperatures. And when we heat the sample to higher temperatures, we populate the sample in upper states. And so when we have higher temperatures, we will see transitions from n equal 1 and n equal 2 and n equal 3. But because we have to heat the sample to see those transitions in the spectrum, those are referred to as hot bands. Okay. Now, again, we note when we talk about spacing between adjacent hot bands that we're talking about 2 nu EXE as a spacing that again allows us, as we noted in the infrared spectrum we discussed earlier, if we calculate the spacing between the lines, we can determine then from that the anharmonicity coefficient for the molecule. Okay, so here's an actual infrared spectrum of CO2. We actually took this, somebody blew into, you can see down here Luis, blew into the infrared spectrometer and we took a spectrum. We can try this, you can try this as well if Bob lets you, and just take the infrared spectrum. You'll remember from carbon dioxide, from our discussions earlier, that it has 4 vibrational modes, a symmetric stretching mode, an anti-symmetric stretching mode, and 2 bending modes, both of which occur at the same frequency. There are 2 degenerate bending modes in this case. What we're looking at here is the bending mode with the frequency here. We'll see the center frequency at 668 wave numbers for the bending mode. Okay. And this would be the n equals 0 to 1 transition. Right, there's our fundamental. If we look over here on the side at lower frequencies, now again, this is a real IR spectrum, so in this case, unlike the graph I drew earlier, we'll note that frequency is increasing here from right to left. So we have lower frequencies over here on the right and higher frequencies over here on the left, and we're plotting 100% transmission just like you see on a typical IR spectra. So a higher peak, a more intense peak, is actually going to be one which goes down farther in this situation. So there's a subtle difference there between what I drew earlier in this video. But nonetheless, we have, at lower frequencies, we have this peak here, and that is the hot band from 1 to 2. Okay? The bending mode vibrational frequency is low enough that when you do breathe into it, there is enough of a population in the n equal 1 state to get a transition from 1 to 2 in the n equal 1 state. So there we have that hot band that appears in the carbon dioxide spectrum. And again, if we took the difference between these two, this peak and this peak, then we're going to see that difference is going to be equal to 2 nu exe for the carbon dioxide bending mode. Now when we have multiple modes, vibrational modes, we're going to note that the anharmonicity coefficient will be different for each of those modes. So we're going to get the anharmonicity coefficient for the bending mode from this, but we won't be able to say anything about the other vibrational modes without making measurements on those modes. We'll also note this structure where we appear to have like 3 overlapping peaks. There's 1, there's 2, there's 3 in the bending mode, is due to row vibrational transitions, which we talked about in an earlier video. The one at the higher frequency, that particular band is the R branch. At the lower frequency we have the P branch, and the central frequency is the Q branch, which remember doesn't appear for diatomic molecules. The Q branch is delta J equal to 0 in the Q branch. The R branch, of course, is delta J plus 1, and the P branch is delta J minus 1. We see that, but we do see those 3 branches there in the bending mode for carbon dioxide. Now if we look at the antisymmetric stretch, which you'll note occurs at a much higher frequency, this, as we noted, is typical. Bending modes tend to be at lower frequencies than stretching modes. So the antisymmetric stretch for carbon dioxide is shown here. We see no hot band in this particular circumstance because the sample is not hot enough to populate significant numbers of molecules in the n equal 1 state, but we still see 2 bands, and we have a P branch and R branch. We don't have a Q branch in the antisymmetric stretch. So much like diatomic molecules where we don't have a Q branch, the antisymmetric stretch does not. Of course, the symmetric stretch doesn't show up at all in the infrared spectrum because the dipole moment does not change during the symmetric stretching vibration. And finally, what we have here is a Raman spectrum. And we haven't talked about the details of Raman yet, but this is actually taken from my PhD thesis where we were looking at nitrogen molecules that were dissociation products from a molecule called azomethane. We blasted the azomethane molecule and caused it to fly apart. We created nitrogen molecules in the process, and then we measured their vibrational frequency spectra that resulted from that. So here we have 2 bands. The bands that are shown here correspond to the n equals 0 to 1 and the n equal 1 to 2 transitions. I've changed the V to an N. We refer to V, and many textbooks use V for the vibrational quantum number. Our textbook uses N. So the one on the right, which is again at higher frequency, is the n equals 0 to 1 transition. The lower one is the hot band that occurs, which is the 1 to 2 transition. And again for this, what we see is the hot band occurs at lower frequency, and the difference between the 2 lines is 2 nu exe. So again, we could use this to calculate the anharmonicity constant for the nitrogen molecule. So this ends our discussion of vibrational spectroscopy. using the anharmonic model, which gives us a more accurate depiction of what we will see in the infrared and Raman spectra. Again, we'll talk about Raman spectra later of molecular systems. I hope you enjoyed. Stay tuned for our next video.